I'll start off by setting the context, and the best way to do this is putting up our generation capacity heat map for the eastern part of the network. So the heat map that you have there illustrates the capacity that we have available on the network currently to accept new distributed generation connections. And the purple color is highly saturated areas where there is no capacity almost available for connections. The red areas is highly utilized, scarce capacity. Amber areas, a little bit of capacity. Green areas, there's some capacity. This is a position of as of January this year. So what you have is that if you apply for a connection in either the purple or the red areas, what you will get back is you're going to get back an offer that involves significant reinforcement that we need to do in the network in order to alleviate the constraints, primarily seeing thermal and voltage constraints. The thermal constraints are more prominent on 132 kV and 33 kV networks, and the voltage constraints on 11 kV networks. So what that means is that what you'll get back is quite an expensive connection offer that involves reinforcement that takes time to build, so there's a time element as well. So this is currently the position. And a significant, if you like, figure to add here is that last year on this network, we accepted and we contracted about 1 gigawatt of capacity in terms of solar PV. If you consider that as of the end of last year, the total UK PV capacity was around 2.5 gigawatts, and we accepted 1 gigawatt within a year. You can understand, what impact this contract capacity and connections have on the network. So this is the context where we operate. We looked and we recognized that we have to look at ways of integrating distributed generation in constrained networks in a cost-effective manner. So in order to do that, if you look at the requirements, is that you need technical solutions that can release capacity within the existing assets. You need to move into an approach where you connect and manage the generator. So you have a method whereby you can offer connections on the existing assets and then manage and operate the output of the of the generator, within the operating limits of the network. So you need to have such solutions. You need communications because you have actors that are dispersed across the network. You need new contracts that you can enter with generators in order to be able to offer this type of flexible connections. We call them interruptible connections. And also you need to have new planning and appraisal tools in order to be able to plan the networks in this kind of generator-dominated world. So we set up a project, the Flexible Plug-and-Play project, which essentially is looking at all of these aspects. Its sole purpose in life is to find ways, and our slogan is to offer cheaper and faster connections to distributed generators in constrained parts of the network by trialing smart grid technologies and new commercial agreements. We started, as Martin described, we started in January 2012, so we have now entered just the third year of the project. Our total budget is just short of 10 million. The Quadrature-booster is a significant part of that budget, hence a separate, if you like, whole day for it. And we have delivered this, and we are delivering this. We've been very lucky to have a very good consortium of collaborators, both industrial and academic, manufacturers, consultants. You will see for today, you'll see during the day that Wilson's Transformers, Fundamentals, Carillion played key roles in delivering the project. So I'll just spend now a few minutes to go through what we set out to do and what we actually have done. So we set out to engage with our stakeholders. So one of the first things we did in the project is to find the generators in the local area, sit down with them, explain what we are planning to do through structured interviews, and get their feedback. So we initially interviewed 20 DG developers. Since then, we've obviously have built a kind of wider stakeholder group, and we've engaged now with over 40 generator developers and other kind of trade associations for generation, and it's been very good in the sense that we are getting the feedback and we are getting the views and the insights which we then can build, and we can come up with a product that meets also the requirements. We set out to look at principles of access. Principles of access is a way that you allocate constraints or curtailments amongst multiple generators if they all contribute to the same constraint. So we looked at, and we are trialing two different methods. We looked at the last in first off, which is a standard way of doing this, and we had previous experience from SSE. And we also developed a methodology called Capacity Quota, which is based on a pro rata access to the network. So everybody shares equally the constraints. So everybody who participates, we've implemented this in March Grid, and we've declared the capacity of 33.5 megawatts is interruptible capacity. So once the constraint appears, everybody who participates in that quota shares a constraint on an equal basis. So two principles of access. We have now offered, we've made 26 offers. We had 7 offers accepted, and we have a total capacity of almost 25 megawatts to connect on the network this year. So it's 7 generators who vary from a half megawatt anaerobic digester CHP to 10 megawatt wind farm. We have solar in the mix, so quite a diverse range of generators. And also we are now connecting generators at LV, 11 kV and 33 kV, which is, all of this generates a wealth of experience and learning for us. In terms of the investment model, we've been doing some work with Imperial College and Cambridge University. Imperial College is building a power flow-based investment model that's looking specific at the area, and we can run some forward-looking scenarios of what investment would we need in the network should X megawatts appear at different parts, different times in the next 20, 30 years. And it gives us the ability to evaluate traditional investment approaches such as net reinforcement to more incremental, smarter approaches. Such as applying dynamic line ratings or curtailment of generation. So this, if you like, closes off the commercial and investment aspects of the project. The 4 boxes in the bottom are summarize the technical platform, illustrate the technical capabilities that we've developed. We have installed a wireless communication network across the trial area. The trial area comprises of 12 sites. It's 2 grid sites and 10 primary substations. So we've developed the communications that link those sites in a wireless manner back to our control center in Fort Hamlet. We have upgraded the RTUs on all 12 sites, and we've commissioned 4 dynamic line rating systems, which have been under trial since September. We have upgraded a couple of our substations with new voltage control systems. We've deployed an active network management system which essentially brings all the devices together and has the ability to control the generators. So if you like, this is the control brain of the operation that delivers the interruptibility that we contractually sign up with. We are also running a couple of trials on looking at new protection scheme that can can help us with some limitations we have with the directional overcurrent protection for those familiar with that issue. So in further, we have also installed the first quadrature booster at 33 kV. The quadrature booster was recognized by our colleagues in asset management as a technical capability that we want to develop as a company. We'll talk about the specific application today, but it has multiple applications and can help manage power flows, especially in interconnected networks. So we found a couple of applications that we could deploy within the trial area, and today we'll talk about the actual site and the actual case study that we decided to go with. And finally, I think that's the unsung hero of this project. mainly because it's complexity and specialization, is the fact that we've integrated all of these devices and we've brought them together under the new standard of IEC 62850. Essentially, all the devices that we have developed, with the exception of the protection scheme, which is business critical and sits on its own, but everything else is actually integrated using IEC 62850, a common language for substation automation. That in this specific instance, we've also deployed it across substations. It's primarily a standard that is a protocol that is used within the substation. We've stretched it outside of the substation.